Thank you, everyone. So, another Kubernetes talk. I've talked to a lot of people already, so you're very familiar with it. So I can skip a few slides, I guess, or go over it a bit quicker. So first I want to talk a bit about Kubernetes challenges, especially in a database or data context. Then about the architectures of Kubernetes underneath, what we need to host a database or some stateful applications on it. Then short introduction what Couchbase is, and then a little bit about Couchbase Operator and a short demo. So very packed. So everyone, I guess, here knows a lot about Kubernetes and why it is so great. I mean, shortens the software development cycle, small independent services, teams which can deploy individually, DevOps, where you can combine everything from development to deployment very easily on a single engineer. Then also improve the efficiency, especially if you have large hardware, that you can combine a lot of services on single hardware, run everything in parallel. And also the continuous delivery. The smaller the application, the better it is to ship increments, while you can just destroy a pod and create a new one. So all very good advantages, right? But there's a few challenges. The first challenge is actually eliminating database silos. So applications usually also need to store data somewhere or somehow, right? So either you do this as seen here in a separate database, which is not in your Kubernetes cluster. So it could be, depending on how big your application is, a very big Oracle cluster if you have one, or some managed service from the cloud, or something on bare metal hardware, which sits in parallel to your actual application environment, right? So that has advantages, has also a lot of disadvantages, because you have then two separate systems. You have to work with the network. Everyone who deployed ever some Kubernetes knows that external networks for Kubernetes environments are difficult to handle. So everything which makes it more difficult to have data, right? Second challenge, avoiding cloud vendor lock-in. Of course, if you deploy in Kubernetes, then you have already an abstracted format where you can easily put your application from A to B, but that's not the case for your database, especially if you have it in parallel or you use something which only the cloud vendors have, like DynamoDB or something like this. So those are real vendor lock-ins you should avoid. So be as open as possible that you can port your application anywhere, on-premise, into the cloud, and so on. And the challenge number 3 is lowering, obviously, your operational costs. So if you have multiple systems in parallel, database, storage, whatever, then you also have to manage it. So wouldn't it be great if everything would be in Kubernetes, your database and everything? That's cool, isn't it? So let's talk a bit about the Kubernetes architecture, what we need to actually do this. So why would you actually extend the Kubernetes stack to have your database inside? Well, if you manually deploy it inside your existing cluster database, usually you also manually need to configure it. You need to maintain it, you need to backup it, you need to do maintenance, whatever, everything manually. So scaling is an issue because you need to have pods, you need to have some synchronization mechanisms, you have to backup and restore mechanisms implemented, everything yourself. But, well, it's not so easy because everything is designed to be stateless in Kubernetes. At least it was for a very long time. So the people were thinking about, okay, if we want to, what do we need? We need an extension. And this was basically a few years ago added into the Kubernetes stack, that you can have your own plugin on top of the stack to provide more services, such as a database. And what does it use? So the core Kubernetes has a few extensions already, right? So it needs to talk with drivers to the infrastructure, to the storage, So that's good if you want to store something, if you can also talk to it. Then we have lifecycle hooks like authentication, creating of admissions, verification, filters, and so on. We have also the upper level, the APIs, where we can talk to the whole stack with it. Also schedulers we need, especially for backups or some jobs we need to run in Kubernetes. Something like a cron job, similar to it, right? This all is already there. And on top, you have your plugins, which can use all of this. So what can you do now? As you know, there is definitions inside the stack already. And these are the default ones, where you can deploy something, create something, and so on. But if you want to put a completely new product on top of it, then you need to extend the resources, as they're called, the custom resources, that you can use that keys to do something and define it in the Kubernetes stack. And this is these are the CRDs, the custom resource definitions. And how does it look like? Well, this is an example of a Couchbase cluster CRD. So all the specs and the keywords inside need to be defined before that you can actually reuse it to deploy it. And the format is a JSON YAML file, similar to what you know already, but using what you actually defined as a provider for this. So this is how one of them looks like. So operators. Deploying something manually was the one thing. So we have this, so we can now deploy something, create something, use the infrastructure, for example, storage, everything you have now in the definitions to define a database and to deploy one. All right. What you didn't gain with this is the control, the automated control out of it. So still, you would need to have some code, some scripts to maintain it, to backup it, to upgrade it, to do failovers, whatever. The concept, which is also implemented since a few years, is called operators for Kubernetes. And they are almost like a fully managed system on top of Kubernetes now. So what do they use? So they have their own control plane and their custom controller. So this is called the operator, which has the logic inside. So everything you would normally do to check a cluster if it's healthy, if you need to do a failover or a backup or how a backup is actually done, the logic is in the operator. And the operator has therefore the access to all the definitions, all the resources, and all the API of the Kubernetes cluster. So what can it do now? It controls and maintains and monitors what you defined. And in our case, a database, which is not so trivial. So a bit of an introduction into Couchbase first, because then I go into details how we do it and what we can do with it. So Couchbase is a NoSQL database, but our specialty is we do SQL as query language. Founded 2011 out of two companies, so you might have heard of CouchDB and Membase. So they got both merged into Couchbase. That's what we are now. 800 people since 2.5 years on the stock exchange, more than 30% of Fortune 100 users. I'm not sure if everyone had heard about Couchbase before. Headquarter in North America, in Silicon Valley. Also here we are in Germany, in Munich, and everywhere on all of the major platforms. The interesting thing about us is when I actually traveled here, throughout my whole journey, I touched a Couchbase database, and no one knows actually. So what did I do? I flew with Lufthansa. So the booking engines behind all of the flights worldwide is called Amadeus. And if you know the 6-digit code you get, right? So that used to be a storage position on the mainframe. You remember? 6 digits, all your booking codes. This is a key which comes out of Couchbase. So this I needed. then I was actually sleeping in the Hilton nearby. So my booking information, everything was stored in Couchbase. Then I paid actually with my credit card, which is an Amex. So all of the transactions which I do go over Amex. And now, afterwards, I will go with Uber to the airport. And the Uber matching and the chat system between driver and the app user, that's running on Couchbase. So throughout my journey, I touch it every time, and no one knows. So it's really a database for the most critical applications, the most demanding applications, because Amadeus, for example, they do at this very second 40 million requests a second from all the travels worldwide, and they serve it in a sub-millisecond response times. That's amazing, but no one knows. So what is Couchbase? What can I do as well? So we're a NoSQL database, so that means we store JSON documents. As query interfaces, we have key value, which is in memory. We have also an integrated in-memory cache. Then our query language is SQL. On top, we have also full text search, vector search, which is the memory for all the LLMs. Then also we have real-time analytics, graph traversal, time series interfaces, eventing, which is similar to triggers, if you know them. We have also a mobile component, which fuels the mobile applications to sync with the database. Then we have different storage engines, more for disk, more for memory. Asset transactions are possible, also joins and everything you know. The cluster map is the keys to success here in the Kubernetes world. I will come to that in a second then. Columnar storage is a new thing, active clustering, workload isolation, and geo-replication. So Couchbase was designed for a cloud-native world. So all the features and services you see here can be deployed individually on a single pod. And this is the big difference to all the other databases, because we don't have a central component, and we do really service and workload isolation, which makes it perfect for Kubernetes or an environment which uses containers. So let's talk about what the operator can do. So you all know stateless applications, they're all deployed in multiple pods, for example. Usually they break down quite easily and it's no problem to redeploy them. But this is also the problem if you have a database, right? If you have central components, then the whole concept won't work. And we knew this, and our approach to development was to have a completely different distributed database with no single point of failure. There is no central component what we have. And the logic is basically in the clients, in the app side. So this makes it easily possible for us to deploy on Kubernetes, because each of the pods can just go down without interfering any of the operations, because, well, there is nothing central which can break. Well, nodes can go down, but there is replicas, so you have continuous delivery of service. So how does an operator look like? Something like this. So you have your Kubernetes cluster with the control plane, with all the API, with the scheduler, DNS. And then this is what we developed. So the admission controller, so that's basically validating the YAML configurations of how a cluster should look like. Also, it takes care of the mutation of the configuration and so on. And then the actual autonomous operator, which has the control of all the pods, of the service, of the storage, volume claims it does automatically, and obviously all the logic which is needed to maintain our database, like how to do a failover, a rebalance, how to scale, backups, and so on. Everything is inside. And then it has to just be deployed in default namespace, for example, and then in a user-defined namespace, you can deploy each individual cluster, which is maintained by a single operator, if you like. And then each node or each worker pod gets its own pod where the database is running on it. And this is what you see here. Completely distributed among 11 nodes here with all the different services spread to different pods over different groups. Very important if you deploy it in regs. So we have a feature called reg zone awareness. If the information, the labels are populated to the operator, then we can basically say, okay, these pods are on one blade, these are on the other one, and the data is distributed so that the whole blade or a rack can go down, and the replicas are still there. So continuous service. Obviously, not sure if everyone knows operators. There is different classes of how good they are. So there's usually 5 levels defined by the Kubernetes Foundation. We have the highest level. Also, a few other vendors have this. But what does it mean, level 5? You need to have the following features. Automated cluster configuration and provisioning, auto-scaling, in and out, automatically based on load. Automated cluster upgrades, so you just need to change a flag that you want to upgrade, it will be done. Recovery, hibernation, so you can just stop it and pause it and then power it up again. Persistent volumes need to be created. Server groups, you need to be aware of them. Cross data center replication, so that's a cool feature, which allows us to have one cluster be replicated to another in another data center or region, for example. TLS rotation, user management, of course, admission and so on, backup, restore, and logging, and a centralized monitoring system. So that's what we can do. So this was what makes a level 5 operator. So how do you deploy it? It's actually just 2 steps, or if you use Helm, it's actually just a single step, where you basically apply the operator and the admission controller to your Kubernetes cluster. That's it. Then you need to create the custom resource definition so that the cluster knows what you actually use, and that's it. And then you need your YAML file, which defines the database cluster, and from there on, you can just use it, and it will be managed by the operator. So what's the benefits? So you have an autonomously running stateful application in your Kubernetes cluster next to your application. So you don't need to deal with the network and everything. They can directly talk to each other. They're actively managed, so you as a developer can just focus on developing and let the database do its thing. It's the best practice of us implemented, so you don't need to be an expert on the database. You just deploy it with these 3 steps. Then you have a production-ready database, actually. This allows also for hybrid cloud and multi-cloud strategies, because with the features like cross-data center replication, you can have clusters replicated through different systems. So that's great. And our best practices is implemented. So it reduces really the effort for you to 95%. So only a few things. Obviously, you need to check from time to time and monitor from outside, but the rest is done itself. How can you try it out? You can just download it from the Couchbase website, couchbase.com/downloads. It's also in the Helm charts available. Also in the Docker Hub, if you want to deploy a single container, no problem. Also in operators like OpenShift, it's available. So it's in the operator hub there. Just use it. There is no enforcement of the license. You can just use it for development, for evaluation, and so on. When it goes into production, then obviously you need to pay some licenses, but for tryouts, everything is free. So now for a quick demo of how this all looks like. So let's up. So this is how an operator looks like. So that's its log, right? So now we'll show you the pods. So kube control get pods. I already deployed the database. It usually doesn't take long, just 3 or 4 minutes maximum if you have the Kubernetes cluster already running. It's very quick, but we're not having so much time, so I skipped this part. Here it's deployed. It's the example ones. So this is my 3-node cluster I have. And you see 2 other things. So the operator itself and the admission controller, which takes care of the YAML configuration, basically. Another one is Pillow Fight. So this is my benchmarking tool. Right now, it fires 50,000 requests per second onto the 3-node cluster. It's having 4 cores and a 16 gigabyte RAM. And it's not maxed out, so I can easily double that, but the single Pillow Fight pod won't do more, actually. So that's my limit. So that's how powerful Couchbase is. So how does the config look like? So if we have a look at the YAML configuration, well, it's as easy as this, right? So you need to create a username password, which is hashed. Then the definition, so the first one here is called bucket, so that's equivalent to a database in relational world. And then the cluster itself. It's very minimalistic here, but be sure everything you can configure in the database can be configured via this file. So it can be quite extensive, right, with everything. Here it's very simple, but it's already good enough for most of the use cases. The others are very specialized use cases, I would say, because the database is tuned already to serve most normal purpose. So you don't need to change much. And what we can see here is size 3, so a 3-node cluster. This is my name, and then the services. As I said, all of the services I showed you, we can deploy on individual nodes or pods. So the data storage individual from the querying interface, from the indexing, from full text search, from analytics. And this is what I can define here. What service runs where. Here in this example, I collocated everything. So data, index, and query run on the same pod, but I could also pull them apart and everything fully automated. If I made changes to this file here, I just need to apply it. Once I do that, it will be done in a rolling upgrade. So your service will still be there, continuous service delivery, but that's everything you need to do, right? Just configure here, apply it, and the operator will do the rest for you. So from operations perspective, very cool. So then let's have a look at the GUI real quick. So that's here. So this is how Couchbase GUIs looks like. And I go to my dashboard. Here you can see that it's doing the 40,000 requests per second. It should be a 50-50 read-write workload, or I think it's 2/3, 1/3 read and writes. These are my 3 nodes, and now I'm going to kill one. So I'm tunneled to the first one, so I'm not going to kill that one. Cube control, delete pod, and my example 4. So that is deleted. So now soon the operator recognizes that something is wrong. So we have a look here at the GUI as well. So there is an unresponsive node. It failed. So also the operator has seen that already. So what does it do now? It waits a bit. Why? Because if you have the timeout too little, then you have the problem that if it's just from a network perspective not available for just a second, then you have these huge failovers all the time. You don't want that. So we have a configurable time, which can be very tiny if you know what you do. Otherwise, the setting could be a bit higher, because otherwise new pods are created, added to the system, failed over, and so on. And this is what it did, right? So I killed the 5. What it did then, it's creating a new one, the 6. So that's what we see here. creating the pod with the software of Couchbase on it, claiming the new volume, restoring it from the others which are still there, rebalancing, that's called, that the data is equalized again, and then adding it to the system again. And once it works, so that's what it does, or it did here. So data is equally distributed across all nodes again. That's called balanced. And we did our failover. So without any interaction. And if we have a look at the dashboard, here you see that we have a drop slightly in requests. But the cool thing is there was no downtime. So even though I killed it, still you could talk and read from the cluster. The client is intelligent enough to read immediately from a replica if needed. And also the rebalance, the adding to the system, everything was done while it was running. So that's amazing. Because usually the databases like MySQL and so on, this is not possible. So this would immediately be a downtime and an administrative task to set up replication again, to restore it. Here it is made to be resilient, made for applications that they're always available. And so this we can also see then in our pods. So kube control get pods. So now we should have the 6 here. Oh, I killed the 4. Never mind. And have the 6th one and working again. So that's all the magic what you can do with an operator. That's it from my side. So if you have questions, please do so. Also, if you would like to connect with me, you can do so on LinkedIn, for example, Gregor Bauer, or you can just write me a mail. It's very easy, gregor@couchbase.com, or you write whatever. All right.
Thank you very much. Are there any questions, folks? Yeah.
Yeah, thanks for the talk. When I deploy a cluster, does every namespace get an operator?
No, you can just deploy it in the default namespace, and then each custom namespace, the cluster you deploy there will be maintained by the operator you deployed in default.
Okay, thanks.
But you can also do otherwise if you like to, because obviously it's another redundancy if you deploy it multiple times. But you don't have to.
Thanks.
More questions? Oh, and back.
Hi, great presentation, thanks. You mentioned about the update, the automatic updates. How does that happen? And is there some control mechanism that we can have in place to force, for instance, a major version?
Mm-hmm. So, I mean, what you would usually do is you put your version control on this file, because this is the definition of your Couchbase cluster. Upgrades pretty much happen like this. You just change, for example, the version number, and then you do your kube control, apply -f, Couchbase cluster, you hit enter, and it does it. So that's it. Because the logic on how to do and what to do is in the operator. And each of the different settings has their instructions built in what to do. For example, when you do an upgrade here, there's a rolling upgrade happening. So a new pod will be added with the new software added to the system. Another one will be killed all automatically until you have everything. And for the rest is either CLI calls, REST calls, whatever is needed to change the settings.
Maybe I misunderstood one of the previous slides. I had the impression that there was an automatic update going on as part of the operator, but that's not the case. You need to do a manual update if you want to update the operator version.
Yes.
Okay, thanks.
But if you say it should update the cluster, then it does it automatically.
Right, and very basic question. When you were killing the node, the new one that was spawning up had a percentage Like, how do you calculate that?
So this is basically the distribution of the data, what you saw. So each server has a chunk of the data. And basically, it needs to be, in the failover case, be restored from the replicas from the others. So we know how much it should be, and this is basically the percentage of how balanced it is already.
Thanks.
Very well.
So, any more questions? Okay.
Do you have any particular requirements for the underlying storage that is, I assume, is used, like a PVC?
So usually block storage works best. Theoretically, it works on all storages, but at lunch we had this discussion. We basically have all the tools to cope with a failed node and failed storage. So if you put something underneath which does that automatically, then it's not transparent for the layer above for us. So I'm just thinking about the NFS, for example. The NFS would then mount, backup, restore automatically things. If you don't know what it does for a database, that's horrible. Because then you would just say, okay, we stop everything now and go back to the one where we know that it was safe and then restore from there. So block storage or something like pure storage, Ceph, what is this? These are the ones we usually want. Block, EBS, something like this.
Yeah, thanks.
Nice. So, okay, last question, and then.
Really, thanks for the talk. I just have a question about the memory usage and the CPU usage. What's like kind of the idle usage and what's the RAM usage here in your, I don't know, a 50K transaction load?
So this is actually system figures of the worker pod it's running on, what you see for CPU and RAM. And what you can configure is basically on the database level, what we call bucket, of how much of your data you want to have in memory. So you see here a resident ratio. And if you create a new bucket, you say basically, okay, each server you set up has like a top limit you can use. And within that limit, you can tell for each of the bucket how much memory it can allocate. And then it's actively managed as a managed cache of how much data should be in. So usually the ones which are new or most used are in memory. Everything else is coming from disk. You can have everything in memory, then you need a lot. Depends on use case, but then you have sub-millisecond response times. The ratio is 1% or 10-15%, depending on the storage engine.
Data, so if I have
if you have X amount of data, like plain on the file system, 1% you need to have as memory at least throughout your system, not on a single node, throughout. But that's the real minimum. You should have, I don't know, 5% probably to be safe.
It doesn't use all the Couchbase overhead, like all the internal services and everything?
So this is just the allocation for the bucket itself. And all the rest, like communication between and so on, is done with the rest. Because when you set up a node here, you allocate like 80-90% of the memory only to Couchbase. The rest of the 10% is for the operating system and other things to be used. Because this also is quite unique, because on the other databases you cannot do this. So this is also the reason why some of the database go over 100 and whatever percentage. They claim whatever they get, and then they can bring down a system. Here it cannot happen, because we block really the allocation, and if it goes beyond, then we reject, for example, requests, but still it works, the database. On the other hand, if you don't have this enforcement, you can bring databases easily down, but we were designed for resilience, obviously.
All right.
Very good.
Yeah, thank you again very much for the great talk.